In 1572, the Danish astronomer Tycho was among those who noticed a new bright object in the constellation of Cassiopeia. Adding fuel to the intellectual fire that Copernicus started, Tycho showed this new star was far beyond the moon, and that it was possible for the universe beyond the sun and planets to change. Astronomers now know that Tycho's new star was not new at all. Rather, it signaled the death of a star in a supernova, an explosion so bright that it can outshine the light from an entire galaxy. This particular supernova was a so-called Type 1a, which occurs when a white dwarf star pulls material from, or merges with, a nearby companion star until a thermonuclear explosion is triggered. The white dwarf star is obliterated, sending its debris hurtling into space. As with many supernova remnants, the Tycho supernova remnant, as it's known today, glows brightly in X-ray light because shockwaves similar to sonic booms from supersonic aircraft, generated by the stellar explosion, heat the stellar debris up to millions of degrees Celsius. In its 2 decades of operation, NASA's Chandra X-ray Observatory has captured unparalleled X-ray images of many supernova remnants. In the Tycho supernova remnant, Chandra reveals an intriguing pattern of bright clumps and fainter holes. What caused this thicket of high-energy knots in the aftermath of this explosion? Did the explosion itself cause this clumpiness, or was it something that happened afterward? This latest image of Tycho from Chandra is providing clues. To emphasize the clumps in the image and the 3-dimensional nature of Tycho, 2 narrow ranges of X-ray energies were selected to isolate material moving away from Earth and moving toward us. The other colors in the image show a broad range of different energies and elements, and a mixture of directions of motion. By comparing the Chandra image of Tycho to 2 different computer simulations, researchers were able to test their theoretical ideas against actual data. They found that it's most likely that the clumps came from the explosion itself. While scientists are not sure how, one possibility is that the star's explosion had multiple ignition points, like dynamite sticks being set off simultaneously in different locations. Understanding the details of how these stars explode is important because it may improve the reliability of the use of Type 1a supernovas as standard candles for cosmological studies. These supernovas also sprinkle elements such as iron and silicon, essential for life as we know it, into the next generation of stars and planets.